Hey everyone, my name is Wenting. I'm from the Department of Mechanical and Materials Engineering. My advisor is Professor Yan Wang, and the project I'm going to introduce today is the recycling of precious metals and perfluorinated materials from fuel cell membrane electrode assemblies. As we know, the global need for energy is growing rapidly, and the clean and renewable energy sources have gained growing attention. Among the fuel cell technologies, the proton exchange membrane fuel cells, which we call PMFC, are particularly suitable for the electronics and automotive applications, and it occupies a very large market. The core of a PMFC is the membrane electrode assembly, which is shown here. It is composed of a polymeric proton exchange membrane surrounded by two catalyst layers and two gas diffusion layers. However, because of the low availability and high price of the platinum group metal catalysts, the original platinum group metal supply chain cannot support the increasing demand. That is why the recycling for fuel cell MEA is crucial for the development of hydrogen energy. Among the current recycling methods, the hydrometallurgical method is adopted in this case, since we could deal with the rest PFAS materials properly. We can avoid the hazard emission of hydrogen fluoride or the direct pollution of PFAS to the environment. Our goal for this project is to develop a fuel cell recycling method to improve the existing method and introduce new techniques to realize high efficiency, low environment impact, low cost, high profit, and also high scale-up feasibility. The first part is platinum recycling. We will firstly remove the GDL layer manually so that the catalyst layer can contact with the leaching solution directly. After that, the rest part we called catalyst-coated membrane is immersed into the dilute acid with oxidant agent. The efficiency of leaching is calculated from ICP-OES, which is over 98%. Also from the picture here, if we sinter the rest membrane, there is no platinum ash left. This phenomenon double proves our high efficiency. After this, we can precipitate the platinum from the leachate in the form of ammonium hexachloroplatinate. The high purity of this product is confirmed with EDS mapping, and the efficiency is over 96%. The next part is to recycle PFSA materials. The delamination step is firstly done by immersing the membrane in water and alcohol solution. The next step is to separate the proton exchange membrane from the catalyst layer for better future utilization. Because the PFSA used in PM and catalyst layers have very different equivalent weights. With the following dispersion step, over 98% PFSA can be recycled. Also, the PTFE can be directly separated from the dispersion. Here is the optimized flowchart of the whole recycling process with the highest efficiency and lowest mixing of products after trying many sequences. We did platinum recycling first because it is the most important process which has the key function, the highest price and profits. If the sequence is changed, there will be PFSA impurities in the platinum leachate. So now we have partly reached our goals. By using a low-cost method, we can efficiently recycle platinum and PFSA with a relatively low temperature, and the whole process is feasible at a larger scale. The product we get, the ammonium hexachloroplatinate and PFSA dispersion, can be used as the precursors for the production of catalyst and polymer membranes. According to the life cycle assessment studies, the environmental impact of the recycling process is much lower than that of the primary platinum production process. Thus, our recycling method is consensus with these sustainable goals: the affordable and clean energy, sustainable cities and communities, responsible consumptions and productions. In summary, we have developed an overall fuel cell recycling process which is feasible at larger scale. And next, the recycling routes can separately recycle all parts of MEA, reducing the detrimental impact on the environment. Finally, we can recycle the platinum catalyst and PFAS materials with a very high efficiency. Finally, I want to thank the financial support from Plug Power, and also thank you for your listening.